Another no problem. Another thing to observe is to look at left multiplication operators. They will play a big role later on, so it's good to have a look at them already. Well, I say left multiplication, but we have commutativity, so it would be the same as right multiplication. So it's just multiplication by a fixed element A. And if you take in compositions of the multiplications operators, well, composition is associative, but it's not always commutative. And if you write out what commutativity of these two operators would mean, well, it looks like this, write out, and that is actually a kind of associativity that you get here. So you can formulate associativity type property of the algebra in being these operators being commutative. And well, two elements A and B are said to operate a commutative. So that's what we will use later on. Okay, so now the formal definition. So a Jordan algebra is a commutative, not necessarily associative algebra with this Jordan identity. And it is a JB algebra if it also has a norm. It should be norm complete, and it should have these three compatibility conditions on the norm. And it is called the JB algebra, Jordan-Banach algebra. Okay, that's the algebra part. Let's now focus more on the order theoretical part. Such spaces turn out to be order unit spaces. So let's discuss very briefly order unit space, because we are probably all familiar with those, or most of us are very much familiar with those. And well, you can find what I'm going to tell in any of your favorite books on partially ordered vector spaces. But well, for reasons of scientific integrity, I have to tell you honestly what book we have used. That's this book written by Anke and me. It's still for sale for a very good price. Okay, okay, let's continue. So we look at a vector space over R, and a cone in that it is a set that is added to itself, it stays inside. It's closed under addition, it's closed under multiplication by positive scalars, and intersected with minus the cone, it's exactly the zero element. And we get the partial order by well, requiring that the biggest minus the smallest should be a positive element, so it should be in the cone. And my notation for partial ordered vector space is that I write V with the cone. But alternatively, you could start with a partial order and define the positive elements that would give you a cone. But I use this notation today. It's called directed if the difference of the cone with itself spans the whole space. It's called Archimedean if every integer multiple of an element, when it's below one fixed element, it can only be less or equal 0. There are different non-equivalent ways of expressing Archimedeanity. This is the one we use here. And what is a vector lattice if every set of two elements has a supreme, has a least upper bound. An order unit, that's an element such, well, I explained it already. For every element, we can get it between multiples of the order unit. And if the space is also Archimedean, we can define a very nice norm that behaves like a kind of maximum norm. That is the order unit norm defined by that order unit. We take the smallest or the infimum of all these scalars for which we have these inequalities. And so these denoted as a triple, so the space, the cone, and the order unit. I do that as notation for an order unit space. And these are always directed spaces. Well, the way that Anke and I like to study partial order vector spaces is by embedding them in a vector lattice and then use lattice theory. And then, well, of course, if you embed them in a different lattice, you want to have the same kind of structures on your original space. That should not depend on the bigger vector lattice that you choose. And the way to get that is that then that embedding should be order dense. So this is that same definition that Anke already gave. So every element from the vector lattice should be the infimum, the greatest lower bound of all elements from the subspace that are above. And then we call it the subspace order dense. By positivity of a linear map, so for embeddings, then something is positive in the original space when the image is positive in the other space. And then, well, as Anke said already, the definition of a pre-reach space is not very interesting, but I can give it nevertheless. So if you have two elements, x and y, and we add an element z, and it is in such a way that we get less lower bounds, then it should only happen if that element is positive. So that's the only way to get here less upper bounds. No need to memorize that definition. The important thing is that those are exactly the spaces that can be embedded into vector lattice bipositively such that the image is order dense. So that is from the PhD thesis of Marius van Haandel, where he did that theory. Well, we call such a vector lattice cover, and there's always a smallest one that's called the reach completion of the pre-reach space. So how exotic are such spaces? Well, not exotic at all. Every directed and Archimedean partial ordered vector space is a pre-reach space, and pre-reach spaces are always directed. So most spaces that you encounter are pre-reach, well, except for all these very beautiful lexicographically ordered spaces that might cause a problem, but Archimedeanity is okay here. So in particular order unit spaces, they had an order unit, so they are directed. The cone was assumed to be, or they are assumed to be Archimedean. So order unit spaces are pre-reach spaces, so we can embed them. And Anke explained that we can embed order unit spaces, especially in space of continuous functions, by using that functional representation. Okay, let us now combine the two. So we had these Jordan algebras with a cone of squares. I repeated here what the definition was. And well, I will always assume that we have an algebraic identity. And well, as I said, the cone of squares is indeed a closed cone. The algebraic identity is an order unit. And so with that order unit, we can make the order unit norm, but it was already a Banach space. So we had already a norm, but it turns out that they are equal. So the norm of A equals the order unit norm. So these are really order unit spaces with an additional product, like here with these conditions. So that's exactly what the JB algebra is. Okay, then we come back to the question that I started with. So we have a nice partial ordered vector space, namely an order unit space. We have a nice algebra, namely a Jordan algebra, and these two structures, well, how are they related? And well, as Anke showed, if you have a vector or atomic JBW algebras, then the order relation is that there are no disjoint elements. And you can have disjoint elements, but then only in the sum decompositions of vectors. So that was the relation that she discussed. And I will discuss the relation of concepts of center. So the algebraic structure gives rise to a algebraic center. So usually you say that they're all elements that commute with all other ones, but everything commutes already. So in the Jordan algebra, that would not be a convenient definition. So we take that operator commuting, that these multiplication operators commute. And the order center, that is not a subset of the algebra, but a set of operators on the algebra to itself, linear, such that they are between multiples of the identity. And then the question that we have here is, how are these two centers related? Is there a relation between those two? This is what we're going to show. Okay, let's have some examples to think of. So these continuous functions with the pointwise product that I discussed, the pointwise order, and then the constant one is the identity, and the order unit norm is then just the maximum norm. And this is a JB algebra, and it's even associative for this pointwise product, so that's as nice as it can be. And you have also these self-adjoint operators on a Hilbert space with the Jordan product, identity operator as the identity and the order unit, we use the operator norm, but that's then the same as the order unit norm for this identity. And as the cone, we use these the cone of squares, and that is being positive definite in this sense. So that's the natural way of having an order on this space here. But this is not the only thing you can have. So Anke had a whole list of nice JBalgebras, even atomic JBW algebras. So for instance, the spin vector, let me mention that. So that's a Hilbert space times the reals. And as product, we have this product here, and 0, 1 is the identity. We can use this as a norm. And the order that we get is the Lorentz cone. So those are everything where the square root of the inner product is below alpha. And if you do this for h being R2, then it turns out to become the circular cone, so the ice cream cone, the usual cone. So that is an example of such a spin vector. Well, so here we stated that if you take the continuous functions, then it's even an associative JB algebra. And well, it turns out that every associative JB algebra with a unit is C omega for some compact Hausdorff space, so that characterizes them. So JB algebra and associative, that gives such a space of continuous functions. Okay, let's first have a closer look at the order center, and then we will look at the algebraic center, and then we'll combine those two centers and understand how they are related. So let's look at the order center, and we can do that for a general order unit space. So let's start with a partially ordered vector space that is directed. So the order center is in a space of operators. I'd like to have that as a partially ordered vector space of operators. So that's why I assume the space to be directed. Then we can look at the differences of positive operators. And then, well, it gives the order, have the difference is positive, maps the cone into itself. That defines a partial order on this space, and it turns out to be a partial order vector space. I think most of us completely familiar. And if the V is Archimedean, then also this space will be Archimedean. And we have the identity operator that is in here because it is positive. And the order center is then the space of all linear operators, and that are between multiples of the identity. And then those are automatically differences of positive ones, so that is inside this partial ordered vector space of regular operators. So you could immediately define it as a subspace of the regular operators, or like this, that doesn't matter. So it's a matter of taste how you would like to do that. Okay, what kind of results would we like to have for order centers? Well, then we look at the nice theory of vector lattices, and we try to see what we can also get for our more general partially ordered vector spaces. So for instance, for our Prairie spaces, or here the order unit spaces. Well, it is known if you take the space of all continuous functions, then an operator is in the order center if and only if it is a multiplication operator. So it just multiplies everything by one fixed function from the space of continuous functions. So then it is if and only if between multiples of the identity operator. And if you have any Archimedean vector lattice, then it can be shown that the order center is always an Archimedean vector lattice. So it becomes a vector lattice again. So in our case, if we have a general order unit space, so no lattice structure at all, does it somehow consist of multiplication operators? Is there a relation with multiplication operators? And is it under some nice conditions a vector lattice or not? So these are the kind of things we could ask. Well, if you have a general order unit space and we want to talk about multiplication operators, we like to talk about functions. So we use the functional representation of that order unit space. So Anke explained that. So we take the set of all positive linear functionals that are one on the unit, so the state space. We take the extreme points of that. We take the weak star closure of the extreme points, and then we can embed V into the continuous functions on this set. by the usual way of taking point evaluations. And well, this is what Caddison did in his 1951 paper, showing also that the embedding is bipositive. But what we know extra is that it is a vector lattice cover. So the original space becomes order dense. And that makes it possible to apply all our machinery of pre-read spaces. So this is bipositive, and the image is order dense. And so then we can more or less translate an operator from V to V into an operator on a subspace of the continuous functions into a subspace of the continuous functions. And it turns out that that is in the order center of V if and only if it gives a multiplication operator seen as elements of that space of continuous functions. So we can translate it to a subset of continuous functions. We can translate the operator as well. And then it is it's a multiplication operator. We can see the function with which you have to multiply is the phi of the t of the identity. So that's explicit formula even for the multiplication function. And so in this sense, yes, our order center consists of multiplication operators. And from that, we can derive some more conclusions. So for instance, that the order center is closed under composition. Okay, that goes directly from the definition. It's a bit complicated. So if it is in the order center between two multiples of the identity, that the same holds true for T. And then we can add here beta I to all sides, then it becomes positive. So then we can multiply this inequality by that positive operator that preserves then the inequality. That's what we have here. And then we can get the ST to one side and all the other things to the other side. And we can estimate then by this multiple of the identity. And we can do the same with the other inequalities. So we get the estimate from below. So here we can see that the composition of two things in the order center is in the order center. We also get commutativity, and that really uses these the multiplication operators. So if you apply a multiplication operator and another one, it's the same as multiplying by the product of the multiplication functions. And well, that is commutative. So at the level of the multiplication operators, it is commutative, and then it also becomes commutative in the original order unit space V. So we get commutativity. With some estimates, we can see that it must be continuous, everything in the order center. And we can also see that the operator norm and the norm induced by the order units are equal on the order center. So if you like a bit of technicalities, then well, enjoy. If you don't, then it's a moment for a short break, probably. Okay, let's see if I still understand it. Yeah, I want to see that the operator norm and the norm induced by the order units are equal. So let's take an operator in the order center. And I abbreviate multiplication function, I just call it F. And well, for multiplication operators, the operator norm is the same as the maximum norm of the function multiply with. That is easy to see. And also, if you take the order unit norm of the multiplication operator, it's also the same as the maximum norm of F. So that is writing out that is not so difficult to see. Well, then on the one hand, that map phi, that embedding is bipositive. So from an inequality like this, we can apply phi, and we can use this formula here. So we can replace then phi of t by the multiplication operator composed with phi. We get this inequality that's written here. Okay, so we can see this as minus lambda times the identity of the element phi of x. So we can see this as of the multiplication operators between two multiples of the identity operator. And that means that Is that what I wanted to say? Yes. So that means that we have the multiplication operator between the two multiples of the identity if and only we have the operator t between the same two multiples of the identity. So that means that the order unit norms induced by the identity should be equal, both for the multiplication operator and for t. This bipositive map is also an isometry because it maps the order unit to the constant function 1. And we have all order unit norms, so then that preserves the unit. And therefore, the operator norm of t is the same as the operator norm of mf. And then we have all equalities that we want. So the order unit norm of t equals the order unit norm of the multiplication operator. That was the supreme norm of the function. And that is the same as the operator norm of the multiplication operator. And that's the same as the operator norm of t. So we get indeed that these norms coincide. Okay, if you wish, you can end your short break here and continue with the next things on the list of the next orange. Center is a closed subspace of the bounded linear operators. That's just straightforward verification. And well, of course, on the order center, we have these norm inequalities because we had them for all operators. So that yeah, so then we get everything together to see that the order center is actually a JB algebra. This also associative because composition of operators, and we have a unit in it, namely the identity operator. And so I say JB then should be complete. So then we have to assume that the order unit space is complete. So then it is everything that makes it nice, and then it must be a space of continuous operators. So this is actually a very nice space, that order center of a complete order unit space. And we also get, if it is as JB algebra isomorph to space of continuous functions, and it's also order isomorph to space of continuous function, that's a vector lattice. So then, then we get that indeed also in this case, that the order center is a vector lattice. So even if that V has no lattice structure at all, maybe norm complete order unit space is enough to get that is a vector lattice. Maybe because it is trivial, that could be. Without the norm completeness, that is not true. Take the differentiable functions or so on. Then it turns out that the order center multiplication operates where we multiply by continuously differentiable functions, and that is not a vector lattice. So we really need something like the norm completeness here to get the result. Okay, that was about the order center. So on such a JB algebra, we also have an algebraic center. And let's now see how the two are related. So see if we can find relations between those two centers. So to remind you, the algebraic center, these are all elements, the elements of the Jordan algebra, such that for every other element, they operator commute. So the multiplication operators commute. That's known to be a JB subalgebra. It is associative, and hence it is also a space of continuous functions. But we don't know that yet that it should be the same space of continuous functions as the order center. Maybe to have an example again, so very simple. Let's take as a Jordan algebra the n by n symmetric real matrices. And then this consists of exactly of the diagonal matrices. So if you would compute that. And the one thing could be if you want to relate the algebraic center by some order object, then the natural thing would be, or at least I naively thought of that, oh, you just take everything that is below multiples of this order unit and it has nothing to do with the algebraic center. So this is not good. So really have to go to the operator. So if we want to see the right structure compare the order object connected to the algebraic center, it's better to look at the operators. That's why we look at this definition of the order center. Okay, so where are we? We are looking at a JB algebra with an algebraic identity. Let's look at the space of all linear and bounded linear operators with the operator norm. And I want to show that the algebraic center and the order center are isomorphic as JB algebras. So we have to construct an isomorphism between the two, so they are essentially the same. And what is it? Well, it is a map that assigns to an element from the Jordan algebra the corresponding left multiplication operator Tz. So that turns out to be the thing that connects the two and preserves all structures. Okay, so we have to check that every Jordan JB algebra structure here corresponds to every JB algebra structure there. Well, many things are simple. It turns out that this map is linear, multiplicative, injective. It maps the identity of A to the identity operator. And it also preserves norms. So this is all kinds of routine to write it out, not so difficult. And so the only thing that remains to show is that it maps indeed into the order center. So these images are all in the order center, and it also gives everything from the order center. So that's the thing to do. And that's a bit involved, but we still have time and lots of energy. So let's go through that whole construction. Okay, so let's see that it maps. First, let's focus on mapping onto there. Okay, no, sorry, I still mean both things. This is general strategy. Then later on I will split the two things. Well, I think at first sight there was no idea how to do it. But well, Mark was in our team and he had an idea how to do it. Namely, looking at extreme points of these things, well, not of the whole subspace themselves, but on the kind of the order, unit order intervals, and look at extreme points of those. And those correspond, and then you can extend it to a correspondence between the two centers. So the idea is to look at extreme points, and the kind of motivating thing is there that if you look, if you have here the identity of a JB algebra, and you look at the interval from 0 to that, so the order interval here, and you take the extreme points of this order interval, those are precisely the projections. And projections in algebra is as if the square is the same as the element. So that gives some way of analyzing what happens with these order intervals. But it can, of course, only work if you have enough extreme points. Only then you can draw conclusions from that. And in general JB algebras, there may not be enough extreme points. But then we look at JBW algebras, then there are enough extreme points, and then later on by a duality trick, we can get it for the JB algebra. So let's switch to the JBW algebras. Although those were introduced by Anke, so we are familiar with those. So what was it? That is a JB algebra, which is also the dual space of some Banach space. So let's consider that, and I will use M to distinguish them from the JB algebras that I then denote by A. How do we get that such order intervals do have enough extreme points? Well, they are convex. And if we can show that they are compact, then we can apply Krein-Milman to get everything, and recover everything from extreme points. So we need compactness for a suitable topology. And well, there are such suitable topologies. So what are these topologies? Well, we look at the state. So it is a positive linear functional that is 1 on the algebraic identity. And we do not look at all of them, but only what's called the normal states. And that's for lattice space people very nice, because those are actually the order continuous functionals. Order continuous in this sense, if you have an increasing net with the supremum, then the functionals should also converge. And as topology, we take that induced by the normal state. So the net converges if it converges under all normal states. And we have a corresponding topology for operators. We say that the net of operators converge in the sigma weak operator topology if for every point x, it converges under all normal states. The normal states separate the points, so that gives nice Hausdorff topologies. And these are the topologies that make it work. So we can. Okay, so then we have here the statements that we do get a compactness. So in the JBW algebra with that identity, we look at the order interval from 0 to the identity, between the 0 and the identity, and we only take those that are also in the algebraic center, and that set is compact for the first sigma weak topology. Then we go to the space of operators. So we look at the order interval between 0 and the identity operator in the space of bounded linear operators on the JBW algebra. And that turns out to be compact for that sigma weak operator topology that I just introduced. Well, you can forget about the definitions, but just remember that there are suitable topologies that make these intervals compact. Then it also turns out that the map that assigns to an element the multiplication operator, so it goes from the JBW algebra to the bounded linear maps on the JBW algebra, that is continuous with respect to those two topologies on these spaces. And then, well, why are these extreme points nice to look at? Well, here is what connects them. So the extreme points of this order interval in the JBW algebra that are precisely projections. That holds true in any JB algebra. And if we take an extreme point of this order interval in the space of operators, then they turn out to be multiplication operators for some projection that is in the center. So with the first thing, we can go from extreme points to projections. So with the second thing, we can go from extreme points for the operator interval to projections. And the projections in the center that will connect the two for the extreme points. Okay, now we split up into and onto. And so to see that everything here is mapped to something in the order interval, so we do it first for one extreme point of this set. Then that is a projection by the previous lemma, but it is still in the center. And then it is known that the projection that is in the center, that the multiplication operator is in this order interval of operators. This is a book of Alfsen and Schultz. Well, the ingredients are there. Then we can take convex combinations of these extreme points. And if we take a convex combination of z, then multiplying by that convex combination, the same as the convex combination of the multiplication operators. So then we can extend this just by taking convex combinations that we also get for those z that we have that the corresponding multiplication operator is in the order interval of the operators. That was compact. So we can get every element as a convex combination of, as a limit of convex combination of extreme points by Klein-Milman. And since the map assigning Tz to Z was continuous for all these topologies, this converges, and therefore we also get it for all elements from these intervals that this is in there. So we get a onto. Oh, that was confused. Into, now we get onto, we do exactly the same game. Now I start with something here, an extreme point there. Then we had a lemma that says that belongs to a projection in the algebraic center. And those are in the image of F of this set. Then we can do it for convex combinations, and then we can do it for limits of convex combinations, and then we get everything by Klein-Milman and the compactness that we had, so then we get the other thing. And if we then combine everything that we have done so far, we get the following result. So M and JBW algebra with identity. Then this map, so mapping an element to the multiplication operator, multiplication by that element. And we do that from the algebraic center to the order center. This map is linear, multiplicative, and isometric, and it is, as we have shown a few slides before, bijective. And as an extra, we have that it's also for these specially designed topologies, it is continuous, and it turns out to be even a homeomorphism for those topologies as well. This is for the JBW algebras, and I started the whole thing for the JB algebras. But well, then we can do some more work. So we take the module of the JB algebra, that is a JBW algebra. We check that everything about centers and so on, all these things are compatible, and then we can get the result also for the JB algebra. So for JB algebra with identity, we have an isometric isomorphism of the JB algebras, the algebraic center and the order center of these two objects. We have also seen already that on the operator center, on the order center, the operator norm and the order unit norm are equal. And also here we have that map is homeomorphism for suitable topologies, and here we have the weak topology and the weak operator topology, and we can combine everything. So the question was, are there relations between the algebra structure and the order structure? And the answer is yes. If we look at the algebraic center and the operator center, the relation is very, very strong. Namely, they are isomorphic in every possible sense you could wish for in this setting. So that works here. Well, instead of this long story, I could also have shown you this slide. So here's everything. So we look at the JB algebra. This is the definition again. Boundary space, commutative product, not necessarily associative, this relation, the inequalities. We have the algebraic center defined by the elements that operate and commute with everything else. We have the order center between two multiples of the identity. And then, well, we had that for an order unit space. The elements in the order center are actually multiplication operators on the functional representation. If it is norm complete, then it is a vector lattice. And we have that there is an isomorphism of JB algebras between the two centers. Okay, and this is really everything I wanted to tell you. Thank you very much for your attention.
Thank you. I see with all this color, that famous functional Dutch architecture didn't have an effect on you, eh? All right. Does anybody have a question? Of course you do.
I had a question. You proved some of the order properties of the center, and I think there you always assumed that you had an order unit spaces. So I was wondering, can you prove some or all of these properties under weaker conditions? For example, that you're Archimedean or directed, or maybe even worse?
That was not enough time to come up with the answer. Well, the proofs that we had, we were careful enough to formulate them in the weakest possible way. So when we now require order unit space, there we really needed order unit space for our proofs. But it could be that there are more clever tricks to work around. I don't think we have counter examples, but we did not really look at that. So if you remember that question for another couple of years, then please ask again.
Okay, anyone else? All right, then let's thank us. No, sorry.
No, it's okay.
So I see that all the first part, we define this GB algebra with norm, and you are using this completeness with the norm heavily in the proofs, or we can take just like partially ordered and replace these relation or this completion by such order completion or something like this.
I think well, I did not check, but I would expect that the norm completeness is quite essentially used in these things. So under all these proofs and things that I told you, there's a lot of knowledge about JBW algebras, and there it really relies also on the completeness for the norm. So if you would like to replace it with a pure order version, then we would have to go through several pages of the books by Alston and Schultz and replace it. So it would be an interesting project, but I have no idea what could come out. So it's yeah, nice idea. So.
Okay. Okay, then let's thank our speaker. Thank you. So it's now we have this bipositive linear mapping, which can take us to real T, not free T. Thank you. Okay.
First of all, sorry for ignoring you. Nice that you're there. Hello.
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 Mm-hmm.
Yeah. I'm sorry. My question is quite late. I've struggled a bit with my microphone. So I was just wondering if
I'm sorry.
Yeah, sorry.
Yeah, I was just wondering if this thing can happen in Banach-lattice algebra. I mean, we have associativity. The thing is at the same time a Banach algebra and a Banach-lattice. So,
Do you know these type of relations between Banach-lattice between the order center and the
Then what would be the algebraic center of a Banach lattice? So you would need some algebra structure as well. Oh, okay. Aha, let's algebra. Let me think. Yeah. I don't know, so I try to think if it's easy to understand or to prove that those should also be isomorphic. Well, I don't see an easy way of doing that. And if you have non-commutativity, might become quite difficult or not true. So I got that.
Okay. I was thinking about that because the definition of the algebraic center here seems to be brought to an associative algebra, like kind of associative algebra, like the set of operators, multiplication operators, something like that. So
Yeah. So also by looking at the multiplication operators, also we translate it to something that is associative but is not commutative. So that doesn't mean that in a Banach lattice algebra it could not work. But maybe I should just say that I don't know. I was thinking about it and I don't.
Yeah. Thank you.
Immediately how it works. And Banach F algebra, yeah. And then it's the same. Yeah. If you have something that is similar enough to a function space, then it should be the same. But only a Banach lattice algebra, I don't know. It's an interesting problem. Many open questions still, I think. Oh, thank you. Are there more questions online?
No, they're asking about the sound of me disappearing sometimes. There's no question. No, thank you. Thank you, Maria.